Hello, welcome back. So previously we've seen the whole way of going from a truth table to a condensed or efficient logical circuit using simplification rules and sum of products. Today we'll try going the opposite direction. We'll try going from a circuit to its original expression. So let's get started. Similar as before, we look at the uppermost layer. Actually, in the circuit sense, we look at the last gate applied, which are these two right here. And this is just a not nor, which is the same thing as or. So we can see this as just a simple OR gate. So we put a plus sign as an OR, and then we look at the inputs to the OR. So the first input to the OR is the upper side of NAND, which is A and B, A NAND B, and the other side is just not C. If you would like, you can apply the sorry, not C. You can apply the Morgan's law on the left-hand side of the equation, which is A NAND B, and we will get not A or not B or not C. Note that the previous expression, this one, isn't exactly a product of sums, sum of products, my bad, product of sums, because this is not a product, is a not of a product, which is not exactly a product. But this one is a sum of products because you can see them as, like, see these as, for example, 1 and A not, 1 and B not, etc. So yeah, so this would be the way to express the given logical circuit using Boolean expressions and the sum of products. Moving on to a slightly more complicated, but I would think a bit more intuitive case is this one. So same workflow. We look for the outermost layer of the logical circuit. We get an OR, and then let's look at what arguments OR is being given. So looking at the upper half of the circuit, we get a AND gate, and the AND gate's two inputs are not A and B. And now we look at the other half of the circuit, which is the lower half. The second argument to the OR gate previously would be the not C gate input. So this would be the Boolean expression or product sum term of the given logical circuit. Right now, I want you to pause the video and try coming up with the Boolean expression for this logical circuit. It's a lot more complex than what we are used to seeing, and I recommend you take your time with this problem and come back whenever you're ready for the answer. Okay, welcome back. So, same workflow. We look at this level, we get a NOR, which is an OR with, sorry about that, with a big knot. That is a terrible knot. With a big knot. So let's look at the two inputs of this NOR gate. Okay, looking here, we get another OR gate. The upper input is a AND. The two inputs of AND is not A and B. And then the other input of the OR is just not C from here. And then on the other half of this OR gate, we have a NAND gate. So we get an AND with a big NOT overhead. And the first input to this NAND gate is the output of this AND gate again. So which is we've seen before, not A and B. And the other half of the NAND gate is you see here is another OR gate, and the two inputs to the OR are not C and D. So there we have it, a kind of complex but still good term of a Boolean expression. Of course, you can try applying the De Morgan's law on this to make it a more standard product of sums. My, sorry, I keep saying product of sums. The sum products terms of this Boolean expression. And that will be it for this video and kind of this unit. We've talked about, in these few videos, we talked about how we can use Boolean expressions to get from truth tables to logical circuits, and we've seen how we can go the other direction in this video from a logical circuit to a Boolean expression. In the next few videos, we'll be introducing an easier way to find such logical expressions, Boolean expressions from truth tables, and I hope to see you around. Let me know if you have any questions, and have a great day.